In an increasingly digital world, our phones and laptops have become almost as necessary as food and water. Every day we rely on these devices to carry out our daily tasks, ranging from the minute to the major. Thus, the computing power of our devices is essential to our overall well-being and way of life. Hence, our topic for today is, why is quantum tunneling slowing down Moore's law? Before we jump into how quantum tunneling is slowing down Moore's law specifically, one should be made aware of what Moore's law and quantum tunneling mean first. Moore's law, at its essence, refers to Gordon Moore's perception that the number of transistors on a microchip doubles every 2 years, though the cost of computers is halved. Stated simply, the speed and capability of our computers increase every couple of years while we pay less for them. Moore first realized this way back in 1965, when noticing emerging trends in chip manufacturing at Intel. With the arrival of integrated circuits, Moore realized that the cost per component was nearly inversely proportional to the number of components. In other words, the more transistors you added to a chip, the cheaper each one got, and there was exponential potential to increase the number of transistors you could affordably put on a chip. Thus, these cheaper, more powerful chips with infinite potential for advancement eventually disseminated into multiple industries in the US. Today, almost every technology we care about, from smartphones to cheap laptops to GPS, is a direct reflection of Moore's prediction that the number of components on an integrated circuit would double every 2 years. Despite Moore's prediction having defined the trajectory of technology and, in many ways, of progress itself, Moore's law is seemingly slowing down now. Why? As aforementioned, given a chip size, the more transistors on the chip, the more powerful the chip is according to Moore's law. Thus, throughout the course of history, engineers have raced to shrink the size of transistors, so more transistors can be fitted on a computer chip. However, as transistors are getting smaller and smaller, quantum effects are becoming a bigger concern, more specifically, quantum tunneling. Quantum tunneling is the mechanical phenomenon where a wave function can propagate through a potential barrier. Imagine there is a quantum mechanical particle, like an electron or a proton, sitting on a hillside. You're sure that the particle can't escape. It's not energetic enough to climb over the hill, so you leave it to its own devices. However, when you go back to check on it, the particle is gone. You find it happily sitting on the other side of the hill, having sneaked straight through it. In other words, the particle, in a sense, has tunneled through the hill, or quantum tunneled due to the laws of quantum mechanics. Quantum mechanics dictates particles do not have a defined location until they are observed. The particle could instead be in many places based on a probability wave function. The particle can be described as an oscillating wave, its amplitude representing the probability of finding it in a certain place. When encountering a barrier then, such as a hill, this wave does not end, but instead travels through to the far side of the barrier. Tunneling is the probability of finding a particle on the far side of the barrier. The lighter a particle and the smaller and narrower the barrier, there's a significantly higher probability that the particle may appear on the other side of the barrier. Accordingly, in the case of your laptop, which has billions of these little transistors to carry out its complex tasks, transistors often are the barriers or gates, so to speak. They allow either the passage of electrons or the blockage of electrons. When these gates are functioning properly, computations can be carried out. However, when a transistor gate becomes too thin, there's a significant increase in the probability that, just as the particle travels through the hill, the particle may appear on the other side of the transistor's gate, even though it is closed. In other words, the smaller the transistor gate becomes, the more likely it is for an electron to ignore the gate due to quantum tunneling. The theoretical minimum transistor gate length limit is 5 nanometers for silicon-based transistors. Anything less than that will be rendered unreliable by quantum tunneling. Even though there is a limit to the gate size of silicon transistors, scientists continue to push the boundaries of computer chip performance so that Moore's law may not go extinct. For one, they have begun experimenting with different materials, such as carbon nanotubes and molybdenum disulfide, that deal with electrons with bigger mass, which allows for smaller gate lengths. Moreover, there has also been a concerted effort in recent years for improvement in the areas of transistor design. Transistor density, improvement software, algorithms, and specialized chip architecture of computer chips have all been considered in regards to wringing the most computational power out of them. Despite all these advancements and ventures in computer chip performance, Moore's law, at its essence, was always about an exponential rate of progress. The idea that with every new transistor added, a richer and better future was being made. Although Moore's law holds true now, there's an increasing possibility that the greatest technological prediction of the last half-century is progressing towards a slow and painful death. However, scientists are fighting hard for the next breakthrough that may turn back the tides of technological innovation. This presentation was brought to you by our team, comprised of 2 commerce students, 2 art students, and 1 science student. Thank you.